Hi, I'm Zach Ross from Caltech, and I was asked to discuss how near-fault seismic stations can be helpful for analyses of seismicity and all sorts of downstream analyses that are derived from those. So seismicity is one of the fundamental data types that we have available to us in earthquake science. It's not a raw form of data, but it is a data product, and it provides all sorts of useful information on fault geometry, particularly at seismic depths, which is very difficult to get otherwise. It allows us to study the interactions between earthquakes, as well as the physical processes that are driving these interactions. It provides a mechanism to track the behavior of a fault zone over time, could be decadal scales potentially. And it allows us, in some circumstances, to infer properties of fault architecture, which we could never make otherwise. But beyond just these types of analyses, it also serves, perhaps more importantly, as the basic input to many downstream seismic analyses. And this includes everything from tomography studies to analyses of earthquake source properties, and you name it. So seismicity really is quite important. And when we talk about faults and observatories, in my mind, there's really only two that exist, at least today. And in terms of the long-term operating ones, so we have Parkfield here on the left-hand side. So there's something like 12 or whatever seismic stations as part of the high-resolution network there that are all in boreholes. And this has been quite transformative for us in terms of our understanding of earthquake dynamics on long time periods, as well as its relation to creep behavior through the crust. And on the right-hand side, we have what I'll just refer to as the San Jacinto Fault Zone Array, which is basically centered around the Anza Gap here in the San Jacinto. And there's something like 25 sensors within about a 30-kilometer radius of this area here. And it's been quite useful in the nearly 40 years or so that it's been operating. And for this talk here, I'm going to use this network in particular as kind of a vehicle to discuss the importance of having near fault sensors. And so to start, I'm going to talk about how we can go about imaging the 3D geometry of fault zones from seismicity. And here, this is just southeast of the Anza Gap. So this is where the fault splits into three subparallel strands. So this is called the trifurcation area of the San Jacinto. It's extremely active, and the seismicity is fairly diffuse throughout this region. It's not very, there's not really any localization or significant localization. And in terms of the fault structure, the geometry and so forth, using this big catalog here for 40 years after waveform relocation, we can see very clearly the behavior of all these damage zones at seismic depths. And so the damage zones are highly lineated, and they have a fabric that's dipping something like 70 degrees or so to the northeast. And so if you were to back project this dip up to the surface, it would offshoot the surface traces of the fault by something like 5 kilometers. And so it looks like the whole system undergoes some kind of major transition from near vertical in the upper 8 kilometers or so to about 70-degree dip below that. And this is consistent exactly with the focal mechanisms that we have here that are also dipping around 70 degrees at those depths. But you might say, okay, well, so what? Why can't we just put out, 1,000 seismometers here over a few months time period and collect all this information and then just do the same exact thing? But it turns out it's not that simple. It really does take decades or more of monitoring in order to get a proper perspective of the seismicity in a region. And I think this figure here is an exemplary case of that, where we have something like magnitude 5 sequences here since 2001. And if you look at their aftershock patterns, so they're color-coded by the sequence, there's virtually no overlap between any of these sequences. And in particular, if you look at the orange ones here, which is the 2010 sequence, it essentially fills out kind of a boundary around the eventual area that aftershocks fill in during this 2016 sequence. And so it's really not all just kind of steady activity over time. It's a much more dynamic system than that. It's much more episodic. And so we need having these long-term monitoring efforts in order to be able to see all this kind of stuff. And if you look at this more regionally, well, all this kind of behavior disappears. So if we average all the seismicity over the entire San Jacinto and the Elsinore system, the rates generally look very steady. So here, even some of the largest events within this region, magnitude 5s, large triggering following Elmira-Kukapa in 2010, these are basically just blips within the broader seismicity rates that we see here. And so if we really want to understand the dynamics of seismicity within these regions, we need to understand and be able to quantify the contributions of the various underlying physical processes to these rates, because we know that it's not just so simple, steady behavior like this. And to give you perhaps a very extreme example, here we have a swarm that we called the Kauai swarm. It started in 2016 and it occurred within this little red box here. So just to the southwest of the Anza Gap and pretty much right in the heart of where this observatory is. And this is among the longest swarms in California history since the beginning of the instrumental era. And it produced something like 15% of all the earthquakes in the SESN catalog during that time. And in fact, the rates for this sequence were so low on a daily level that it took about 1.5 years before we recognized that the rates were sufficiently elevated over the previous several decades. And that's because the nearby San Jacinto background activity is so dominant that it kind of masked all this stuff. But then we started to track this and look at the behavior of the sequence in much more detail. And so having all these near fault sensors here allowed us to see some pretty cool stuff. In particular, I'm going to show you the spatial temporal evolution of this. So here we have a color scale that goes from 0 to 4 years for this sequence. And you can see that the sequence nucleates right in this spot here. In fault parallel cross section, you can see that this region where it starts is on the order of a few hundred meters only. And it undergoes this very slow radial diffusion pattern away from this point here over the 4 years time. And it's growing at a rate of about 5 meters per day. And it's not within a volume. Incredibly, this is all happening within a very localized fault surface here that's on the order of about 50 meters wide or less. So it's comparable to the lateral location error in these in this catalog. And so you might think, well, how common is this? If it's the longest swarm or among the longest swarms in California history, if we put all these near fault sensors out, are we really going to capture anything like this again? And it turns out that, yeah, you probably will, because now that we knew that this occurred, we started to look for more evidence of these types of patterns, and we found another 91 of them. And so here we have colored sequences indicating the duration of different swarms that were found over the 12-year period that we studied, going from 6 months up to as much as 6 years in some cases. And so there's nearly 100 of these, and they occur all throughout this broader kind of region in between the San Jacinto and Elsinore fault zones. And this is an area that is not traditionally thought of as a swarm producing region. And yet here we have a bunch of very slow growing swarms that were really not known about in the past, except for a handful of very unusual cases. And so we can look at some of these in detail, and to just kind of inundate you with data, here are 20 of those 92 swarms, where the timescale on each of these is 12 years from 2008 to 2020. And you can see that there's lots of different examples, and they're all happening at different times. And so some of these are short or so, they're maybe a year, and then others are, like this, where they last for 6 years or longer. And one of the characteristics of essentially all of these swarms is that, number one, they don't follow a Mori law. And when they're not active, the entire spatial region around them has virtually no seismicity either before it or after it. So these are highly episodic in nature. And they constitute a remarkable 26% of the total seismicity in this region. And this is a very active region to begin with. So this is a pretty surprising finding here. Now, we can take these, and since we have a lot of sensors that are very close by, we can relocate them very precisely and look at their spatial temporal evolution. And it turns out that about 50% of them, so they have very clear migration patterns And so these are just four examples to exhibit diversity or to demonstrate the diversity that we see, where we have radial distance versus time here. And this is going up to several years, where we expand a distance of about 1 kilometer during that time. So these are very slow growing, and many of them have clear back fronts behind them, which indicates that there's some kind of shut in, and this diffusion process continues to happen away from this point slowly over time. And we see this in many, many, many examples here. And again, these are very, very slow growing. So this translates into a permeability of something like 10 to the minus 18 meters squared, if you were to fit that type of model to these observations. And if we take all this stuff together, we can actually assemble a timeline, which we couldn't do unless we have a 12-year or longer data record. And we can see that these swarms are essentially active at all times during the 12-year study period. And if these are related to fluid injection transients or whatnot, that would probably indicate that this is a very important process for transporting fluids through the crust here if they're continuously happening throughout this broader region. And this is very different from these regional average rates that you see over here, where it basically looks steady over this entire region. So in reality, at a very localized level, you end up with processes that are highly transient in nature. So looking forward, regional arrays are fantastic for many different applications, but I think having permanent fault zone observatories is going to be critical to advancing our understanding of earthquake processes. And short-term deployments can only capture short-term processes. So if we want to go beyond this, we need longer-term observations. And I think this is going to help us move towards a more complete understanding of fault architecture at seismic depths, the physical processes behind all this stuff, and the spatial temporal patterns of earthquake sequences. And so thank you very much. I look forward to the discussion.